get up and running again. Retired a couple of months ago, so I'm not in the classroom anymore, but I have purchased a whiteboard, and it's a little flimsy. I got a new computer now, and we'll see how it comes out in terms of focus. And if it works, it works, and if it doesn't, it doesn't. We'll see. So this lesson set is something that I put forward to a class probably after 2 or 3 weeks of instruction, 38 questions. I'm going to do 19 today and 19 tomorrow, and then take a day off, and then do another lesson set, half that day, half the next. And not trying to teach any particular topic right away, just starting conversations, product rule, quotient rule, chain rule, and we'll then work with them over the course of 40 or 50 lesson sets. And I think that serves you better in terms of long-term memory, because if you do 20 problems on the product rule today and 20 tomorrow, and then you move to something else, a couple of months later you're wondering, geez, what's the product rule? So long-term memory is served by constant repetition, constant working with the topics, and that's what we'll try to do here. All right, so I strongly suggest that before jumping into this video that you've done the other 4. I haven't looked at those recently. Been some health issues, and just haven't been available for doing any of this work. But if you can't get into a classroom, or if you're having trouble with math, you might want to try this process. It's been my belief that for a long time that if you do 4 things, a couple minutes each day, and 4 days later you do it for 4 days in a row, usually a lot of math starts to make a little more sense. So we will be developing these problems geometrically, numerically, so on and so forth, but Rome wasn't built in a day. So I'm just going to start some conversations and continue them. All right, so I'm rambling. Let's just get at it. First problem, hopefully you can see f of x equals 5 to the 7th root of x to the minus 3, and we're going to find f prime. F prime of x. Well, the first thing you want to be able to do is understand that you can rewrite this as 5 times x to the negative 3/7. All right, now we can multiply negative 3/7 times 5 minus 15/7, and we can subtract 1 from 3/7, which makes it minus 10/7. And now I can erase that. And this is a very flimsy board, so bear with me. This is low budget. All right, secant cubed e to the 4x. I'm going to rewrite this as bracket cubed. All right, so we have the cubing function. Derivative of the cubing function is 3x squared. The secant function, which is secant x tangent x. You can get a cheat sheet with you when you're doing your homeworks, because just look at it and you'll know the derivatives. I'll try to develop them as to why they are what they are over time. And then e to the 4x, the derivative of e to the x is itself e to the x. So the chain rule is involved here. I don't think you can understand the chain rule. It's one of the hardest things to teach, I believe. I have a video on the chain rule called the lens, the chain rule via the lens of integration. And we're not going to look at it from an accumulation of area standpoint quite now. It's pretty early in these lesson sets. But I'll just do it out for you. So cubing becomes 3 times something squared. Secant becomes secant tan, so times secant parentheses tan parentheses. E to the 4x becomes itself times the derivative of 4x times 4. All right, so this is a little awkward right now, but I'm doing the cubic with respect to where I am at a particular instance, and that is given by secant e to the 4x. Now, once I've done the cubing, then I got to do the derivative of secant with respect to where I am on a curve, e to the 4x. I'm not teaching this at the moment, I'm just showing. And then the derivative of an exponential function has as a kernel itself, right? So 2 to the x would have 2 to the x in the taking a derivative, but the ln of the base and the ln of e In this case, the ln of e is the exponent you put on top of e to get e, which is 1, so we can ignore that. But where I am getting the exponential change depends upon this function 4 times x, and that's changing at a 4-to-1 rate. I saw a Charlie Chaplin video one time where he was on an assembly line and the owner of the factory turned the assembly line up faster so they'd get more production, and that always comes to mind when I look at the chain rule. But we will, in a month's time, explain why it works. All right, product rule, x squared times sine x, so what's h prime? Well, go to the playlist, look at the length times width geometric video, and you will see a layering of L prime W, boom, and W prime L. With a little bit of error there that as you use a Phillips screwdriver disappears because the accuracy comes from the limiting process. All right, so do the derivative of the first function, which is 2x. Derivative of x squared is 2x. Multiply it times the second function. And then add the other layer, which is the derivative of the second function. The cosine is the derivative sine times that side of the rectangle. All right, so that's just a quick product rule. Get rid of that. K of x equals minus x over 5 plus e. I like to ask this at some point after a few weeks in a term because I want you to tell me what kind of function that is. Well, I hope you say linear. Remember, you're pausing the video because this could have been written as minus 1/5 x plus c. E is not a variable. It's a constant, although it's irrational, just like pi. Okay, if I had pi here instead of e, we could say basically adding 3.14. Right, so the derivative of a constant is 0, so that derivative becomes the slope of the linear function. So this function, if you went to some table values, and I encourage you to, take some jumps, you're always going to get a down 1 to 5 ratio of change. All right, much prefer to have Rene Descartes here and moving around the classroom, but not happening today. Quotient rule, low d high minus high d low over low low. So the derivative of m is low. D high, we talked about e to the x as its own derivative. That's why it's such a powerful exponential function. You can write all the other exponential functions in e notation, and that's practiced in those first 50 lesson sets from Algebra 1 to trig. Low d high minus high over the x. D low, 3x squared times 3x squared over low low. Low low is a squaring process, and you got a little jingle there. And you can go to the playlist, and I'm sure I've done something with the numerics, and yeah, I think I did it geometrically as well. So there's your homework on the day off. Go to the playlist, figure out why these things work. All right, we've got P of x, I'll write it up here because it seems like the video is not capturing it at the moment. Minus 2x to the minus 6. So what's that derivative? Well, first thing you want to do is rewrite this as 3x to the 6 over x squared. That's hopefully part of your foundation, knowing that that's true. So that's 3x to the 4. So what is p prime? P prime is 12x to the 3. All right, one more here. On this side of Olivia. So we've got p of x defined to be h of g of f of x. And this is really spelling out the chain rule. So we have to look at this function and the rate at which it's changing. But where are we on the curve? That's determined by g of f of x. Now that's going to get multiplied times the derivative of g with respect to where you are on that curve, the f of x curve. And then, of course, you got to take the derivative of f of x. Okay? Now, I did a chain rule with, I think, the sine of x squared. All right, that would be good for you to watch because it'll strengthen your understanding of a radian, and you can see the numbers work. And I think I did an estimate of what the rate of change would be at that instant. And I think I got pretty close, so you might want to look at that. There's a lot of work to understanding this stuff conceptually, right? Other than just pure memorization. Pure memorization will get you a nice grade probably for, college purposes for those of you moving on. But understanding what you're looking at takes a little reflection. All right, so here we have a derivative is itself. Well, we just talked about that 5 minutes ago. What derivative is itself? Y equals e to the x. And so y prime is also equal to e to the x. And whether I double this, 2e to the x, then the derivative is 2e to the x. All right? So constant, multiplier. If your first job gets you $10 an hour and I double your wage, I think you got a good feeling for the rate of change coming into your pocket. Yeah, 20 bucks an hour. So y equals 2e to the x, its derivative is also 2e to the x, and so is its second derivative, which could have been written as y double prime. And a 0 gets you 4, so therefore your answer is 4e to the x. Derivative is 4e to the x. And second derivative is also 4e to the x. Okay, so what's e to the 0, 1? 1 times 4 satisfies that. And this derivative is equal to y. All right, so let's get rid of that. Where am I? Can you see what I wrote? I'm not sure. Did I do it in a place you could see? Okay, let's bring things this way. All right, I think we're up and running. Equation of line tangent to the cosine function. Well, the cosine function, the derivative of the cosine is minus sine. And we're at 5 pi over 3. So you should have your circle. You should be able to draw a triangle. You should know where 5 pi over 3 is. The width's a half. Height's negative root 3 over 2. And that distance, by the way, if this is a unit circle, if that's a 1, is about 1.05. So just a little bit longer than the radius, right, would be a pi over 3 distance. And from 5 pi over 3 to 6 pi over 3, you've traveled 3.14 divided by 3 units. Another way of measuring degrees is using the circumference of the circle. So, what is the sine? Negative root 3 over 2. Therefore, the equation of the line tangent, the ELT, starts with the slope of positive root 3 over 2. X minus 5 pi over 3 plus a half, because that's what the cosine value is. Now I will draw 1 period of the cosine function, just to give you a feel for this. Height of 1 here, down to negative 1, back up again. We are in the 4th quadrant, right about there, halfway up. And does it look believable that you're going up at root 3 over 2, which is approximately 0.87? Hope so. Not the best drawing. 1 to 1 might have looked more like that, so 0.87, probably a little more like that. So it's not the greatest drawing, but hopefully it hits the target. All right, so now that's number 9. That's out of the way. Position function. I like to teach calc using Root 91. I think if you looked at the first 4 videos, you saw that drawing already. So position, t cubed plus 3t squared plus 14 minus 5. At t equals 10, where is my position? Well, let's write x minus 10. Plug 10 in. 1,000, 1,300, 1,340, 1,335. So plus 1,335. Grandma's somewhere way north, up in that woods area up in Canada. I hope they still like us. All right, and so what's the derivative? The derivative is 3t squared, derivative of t cubed. 3t squared becomes 6t plus 4. And so let's drop a 10 in there, 364. I think I did that right, under 364. Okay, so this function here, t cubed plus 3t plus 4t at x equals -1, we have a point of inflection. We could graph it, but it's going to look something like that. Maybe it's, I don't know what the slope is, c minus 3ah squared. I won't take time to do that. That's a whole nother topic that's nailed in the first videos, first 50 Algebra 1 through trig videos. All right, so I don't think I have to move the camera now. So if I put a 2 in, it's undefined. So what's the limit as x goes to 2? Well, it's not what happens at 2. We don't care what happens at 2. We want to know as we approach it. So let's put 2.001 in here and think about it. Well, if I subtract 2, I get 0.001, and if I cube that, I get what is it? I think it's 0.000000001. It's pretty small, but it definitely goes into -1 a lot of negative times. So 2.001 is starting to give us a sense of we're heading to negative infinity. Now what happens if I put 1999 in there? Now throw another 9 in there. Well, I get -0.001 cubed is a -0.001, and that's going to go into this a lot of positive times. I don't think I'm headed to the same place. So we say it does not exist. Okay? And this has got asymptotic behavior at x equals 2. On one side I'm going to positive infinity, the other I'm going to negative. So on the right side I'm going to negative, on the left side I'm going to positive, so we say it does not exist. Alright, going just 19 problems here, we're getting there. Hopefully you've done enough graphing of rational functions to know that as you go to infinity, teachers like to use bottom heavy as a term. I don't like to use those terms. I like to say that as you put bigger and bigger and bigger numbers, then this term, 7x cubed, begins to dwarf all these little guys. And 5x squared begins to dwarf all those little folks. And we could plug infinity in and do it algebraically. Right? We can divide the infinity squared out of this, and you got 5 over 7 times infinity, which means this number is getting really, really big. It's not going to fit into 5 much at all. So it's going to 0. And hopefully you knew that for the irrational functions work anyway. All right, x squared might go up like that. X cubed might go up like that. And when I'm here, that y value is significantly bigger than that y value. So this tall one isn't going to fit into that. And the farther I go to the right, you start to get into why L'Hopital works. But I don't want to talk about L'Hopital until the end of the 50 lesson sets, because I think it interferes with your conceptual awareness that we would get from a problem like, I haven't got one on here, but I'll have one on there probably on the next lesson set. So what do we got here? We got something you can't see, so let me put it over here. The limit as x goes to -2 of x squared minus 4 over x squared minus x minus 6. So if I put -2 in right now, I get 0 over 0. That's a bad thing because it's undefined. Okay? It's actually where the two graphs intersect each other on the x-axis. But let's factor. Okay, this one is x plus 2, x minus 2, and this one is x plus 2, x minus 3. I'm sorry I erased it, but pretty sure that's correct. So now what happens when I put -2 in? Well, I can simplify this now algebraically. And so when I put -2 in, I get -4 over -5, which is 4/5. So this is actually a rational function, asymptote at y equals 1. At +3, we have asymptote, throw a 0 in, 2/3 right here. And as I +2 gets me 0, so not drawn to scale. But over here at -2, I have an undefined situation, so I have a point of discontinuity. But as I look at it numerically, I'm going to that same altitude for both directions, so it does exist, and it's actually that height, because this is y equals 1. Okay, so hopefully some review there. And now we have 4 more problems. So you're going to get a little practice here with a little integration. We're going to integrate from 1 to 9 the square root of x dx. What are you looking at? You're looking at the square root function. And you got a 1 here. 1's probably closer to here. 1 there, a 9 over here, something like that. And I'm looking at the net change. Well, the first thing I can find is, well, square root of x could have been written as x to the 1/2. So when you take a derivative, you multiply and drop down 1. Integration is the inverse of that. So we're actually going to add 1 to the exponent and then divide by that. So really we're looking at x to the 1/2 plus 1 over 1/2 plus 1 in this instance. All right, so that becomes 2/3 dividing by 3/2 is multiplying by the reciprocal 3/2. All right, and so when I drop a 9 in, I'm really looking at the area from 0 all the way over to here. And then when I drop a 1 in, I'm taking away this area. All right, so that I get this area here. All right, so a little math here. Square root of 9, 3. 3 cubed, 27 divided by 3, 9. Times 2, 18. Minus, drop a 1 in. And that's 2/3. And so 18 minus 2/3 is 17 1/3. And that's this area right in here. Now, that's a height of 3. From 0 to 9 is a big time error here, right? But you could get an approximation. I suppose we should do it just to 1. Let's just do it to 1. So that's 8 units times 3, 24, and this is all error. So is it believable? I hope so. And so I'm throwing a rectangle in there because you kind of prove integration with rectangles, which are called Riemann sums. And the more rectangles you put into that picture, the more you can get rid of the error. And we'll do that probably on the next lesson set. So dy dx equals, so this is a derivative, dy dx, the same thing as saying y prime. There's different notation systems. And I'm giving you x cubed minus 5x plus 2, which is a cubic in graphing form. It'd be nice to analyze it from that perspective. But right now, y of 0, initial condition of 0 gets us 10. So I'm going to integrate this. I'm going to move the dx to this side. And I'm going to integrate. All right, and if I integrate this side, I'm going to get y equals with a c, and the c's can be moved to the other side. So where did x cubed come from? It came from x to the 4 over 4. Add 1 and divide by that number. Minus 5x squared over 2 plus 2x plus c. And now if I put a 0 in, I can see c is 10. And we just solved a differential equation. I mean, there's whole courses in college just on differential equations. Again, not necessarily teaching anything at the moment, just showing, getting the conversation started. We'll draw pictures as we get a little mechanical prowess. We'll draw pictures and geometry. We'll look at it from many perspectives. All right, 15, I just did. 16, the integral from 2 to, I'm going to change it from 2 to 3. All right, because I think my classes would be more familiar with that. 1 over x dx. Now that's the same thing as x to the minus 1. So if I add 1 and divide by that, I'm in trouble. I can't use that form of taking a derivative. So you have to recognize this. All right, and if you did the earlier lesson sets, I do believe I've already talked about it. That's the ln function. How well you can graph the ln function, I don't know. But if you need to do some remedial work, go to the playlist, the exponential and log playlist, and look at rapid fire graphing of e to the x and ln of x, and maybe you'll pick up some skill. All right, so I'm going to go from 2 to 3 in this case. Why did I pick 2 to 3? Because the ln of 2 is 0.7, the ln of 3 is 1.1, which means our answer is going to be approximately 0.4. Exact answer is ln of 3 minus ln of 2. A quick sketch of the ln function. Here's the x-axis. So here's 2, here's 1, 1 gets you 0, the element 1 is 0. So that's a height of 0.7, and 3 is a height of 1.1. So what would that width be? 1 times 1.1 is a big rectangle, 1.1 unit of area. A good drawing would say that this is a big time overestimate. So is it believable? I mean, a trapezoid would sure be a whole lot better, right? So 1/2 times 0.7 plus 1.1, right? The width divided by 2 times the altitude on the left, altitude on the right. That's 1.8. 1.8 cut in half is 0.9. I think the drawings should be probably a whole lot smaller like that, probably. So I don't think it's the best drawing in the world, but that the ln of 3 minus the ln of 2 is the ln of 3 halves. And in the first 50 lesson set, we wrote 3 as e to the 1.1, 2 as e to the 0.7. And so what does that equal? E to the 1.1 minus 0.7. So that's 0.4. E to the 0.4, I guess. I'm rambling here. I better be quiet because at this stage, I haven't done this in 10 years and I think I'm misleading you. So the integral of 1 over x comes from the ln function. The derivative of ln is 1 over x. And back it up a little bit to the first 4 videos and hopefully said something that makes a whole lot more sense than I did 2 minutes ago. All right, last 3 problems here. 16, 17, and 18, I think. 17, 18, and 19. All right, without my glasses, 17. Yeah, where are my glasses? All right, I'll do it without the glasses. So I've got a function, derivative of f of x, with respect to x, is defined to be x squared times x plus 5 squared times x plus 4. All right, so the derivative of f, big F, little f, f prime, the derivative of f means we're looking at acceleration. All right, and let's just take a quick look at a function like x squared, whose derivative is 2x, whose second derivative is 2, which is always positive, and x squared is always concave up. So if I want to know when this is concave down, I don't even think I told you what we were trying to find that. If I want to know when that's concave down, it's when the second derivative is negative. So hopefully you're coming into the class with some algebraic skill. So at 0, there's no sign change. At -5, there's no sign change. And at -4, there's a sign change. Now, if I put a real big number in, I get a real big number out. So I've got something that looks like that. And I'm not sure that, yep. Oh, so that was a 3. That's all right. This is what I wrote for this particular problem. It's a little different on the sheet. So where am I negative? Well, I'm not negative at, what was that, -5? Right, -4 and 0. So technically, I'm not supposed to write negative infinity to -4, but negative infinity to -5 union -5 to -4 is the interval notation that hopefully paints the correct picture that I've shown you there. All right. Now, if I'm making any mistakes here, you let me know. I always make a mistake or two as I lose skill as I get older. And as I'm talking, I lose track of what I'm even talking about half the time now. But hopefully giving you some practice, especially if you can't get into a classroom somewhere in the world. You can do these lesson sets. All right, average rate of change for y equals x to the 4th. And I'm going to go from 2 to 4, I think. From 2 to 4. 2 to 4. All right, so x to the 4th, very similar to x squared. But in order to see this, I'm going to do that. All right, because I want to put a 2 in to get 16. I want to put a 4 in. 64 times 4, I think, is 256. So what's the average rate of change? It's the slope of the secant line. And so what is that slope? y2 minus y1. over x2 minus x1. So 256 minus 16, 240 divided by 220. So the average rate of change from one location to the next is going up at 120 to 1 on average. Now, closer to 2, I'm going up at a slower than 120 to 1 rate. At 4, I'm going up at a higher, right? 4x cubed is the derivative of x to the fourth. So at that instant, I'm actually going up at 4 cubed to 256 to 1. All right, so, all right. Yeah, I'm getting tired here. All right, last problem, 19. For the given interval, what x value produces the same rate? So where am I going up at 120 to 1? Somewhere in here, right? Somewhere in the interior. Now, this is the mean value theorem for derivatives, which is basically like saying, okay, it's 90 miles from here to Boston. It takes me 2 hours to get there by car. My average rate is 45 miles an hour. Now, the mean value theorem for derivatives says if you know, I've got a derivative, a continuous function from 2 to 4, and I do. 2 to 4, it's continuous. And if it's differentiable everywhere, and it is, it's differentiable everywhere on the open interval, then there has to be some point in time where, in my example, my car speedometer reads 45. Okay? My velocity has to be 45 miles an hour at some point. I can go slower, I can get in traffic, but if I was always going faster than 45, I'm in Boston Harbor. And if I was always going slower than 45, I never got to Boston. So, there's got to be some place here. And I already just found your derivative, it's 4x cubed. We want to know when that equals 120. And that's doing the mean value theorem for derivatives. And I think if you hear that 50 times in a row, you're going to own it. So, 4 goes into 120, 30. So I got the cube root of 30. What's the cube root of 30? A little bit bigger than 3. The cube root of 27 is 3. So somewhere a little bit bigger than x equals 3, I'm going up at 120 to 1. All right, and then I'll do the second half of this worksheet tomorrow because this probably took a half an hour. And hopefully upload it. And if you can't see and it doesn't work for you, write it in the comments and then I won't do this anymore. I don't have the computer I worked with for the last 20 years or so. And I don't have that classroom to put the problems on the board. And I don't know how this is the focus of this, you know, newer computer. It should have gotten a Mac because that's what I worked with for 20 years, but I'm working with a different one. And we'll see how it goes. And if it's still helpful, then I'll continue. And if not, retirement. All right. Hope everybody's doing all right.